You are welcome once again. Today we'll be looking at continuous probability distribution. You know, in the last 1 week now, we have been talking about the relationship between probability and statistics. We started with what probability is, and the different type of, we actually discussed probability distribution and the different type of probability distribution, that they are broadly divided into two types: discrete probability distribution and continuous probability distribution. And we said that for discrete probability distribution, that for discrete variable, that is, you are able to know the different categories of the outcome. You can know the different categories of the outcome of the variable. If you can know all the different categories, you can actually calculate their probability. So for discrete probability distribution, it is possible to know all the different categories of the outcome of the variable and their probabilities. So discrete probability distribution is the list of all the categories of possible outcome of a variable and their probabilities. That's discrete probability distribution. I will give example: Bernoulli distribution, binomial distribution, Poisson distribution, geometric distribution, negative binomial distribution, hypergeometric distribution. We talk about those different types of discrete probability distribution on Thursday last week. Today we want to quickly look at the other side, the continuous probability distribution. And this type, it is not possible for you to know all the different categories. So if you cannot know the different categories of the outcome, all the possible outcomes, cannot know the possible outcome, it is not possible for you to know all their probability. So for continuous probability distribution, you cannot know the probabilities of all the different values. You cannot know. An example, we have them: normal distribution, chi-square distribution, T distribution, then F distribution. Then we still have some, but these are the common type, because the other type we talk exponential is a form of continuous probability distribution, but you know, they can come as a form of transformation of normal distribution. Just like the way we discussed the important, the commonest discrete probability distribution, we discuss the commonest continuous probability distribution. There are different, in fact, the list of probability distribution is infinite, because you can describe many different new ones as people, intelligent people, think of the way to explain national phenomena. They try to come and describe a new probability distribution. But this common one, actually, you can actually use them to explain common phenomena. Most of the common phenomena you want to explain, you can use the common probability distribution. And we have said it, I said it also, so that the most important distribution in research and statistics is normal distribution, and it's a form of continuous probability distribution. And after normal distribution is binomial distribution, and binomial distribution is a form of discrete probability distribution. So we see have some. You will see out of these four, you will see most phenomena, most variables follow this normal distribution in their natural state. But you can talk about a variable follow normal distribution, but chi-square distribution, T distribution, F distribution is the sampling distribution of those variables that follow this distribution. So what really happens is that normal distribution is the one that is, actually naturally, but underlying the normal distribution are all these, because they can approximate normal distribution. All these other continuous probabilities, even the binomial, or even all the discrete distribution, the sample size is large, they can follow their sampling distribution, will follow normal distribution. Now, when we continue talking of continuous probability distribution, example like blood sugar, weight, these are continuous variables that can assume, they cannot assume, they can assume integer, but that's not the only, they can also assume decimal. So when you have something points, 60 point this, 60 point this, it cannot, it's not discrete, it's something that is whole number or anything categorical naturally. Categorical variable, quantitative variable that only integer. Integer means whole number. They are the one that follow discrete distribution. But anything that has any quantitative variable can have decimal, that can assume decimal, follow continuous probability distribution. I want to quickly look at normal distribution. So by next week, we look at, yes, the next lecture, that will be Thursday, we'll look at chi-square. By next week, we'll look at, T distribution, F distribution to unpack some of the secret behind this distribution. They are simple, just for you to understand. Once you understand, you'll be able to conceptualize situation where you use all this, you apply this probability distribution. As I've said before, no statistic without probabilities. Probability that theorize about the variable phenomenon you are studying. What statistic does is to help you when you collect the data about the variables, the phenomenon, you help explain it. But how they are in the population is statistics that is probability that can explain. They give you a glimpse of what is happening in the population. It's probability. What statistic does is that when you have used probability to at least to bring the value of subset of the population, the value of the variable, the statistic, if you explain how they are related, you explain what you are seeing. You take probability and it explains within the framework of the model, the framework provided by probability. Now look at normal distribution. We already no doubt those things that follow normal distribution naturally, they are continuous variable. They can assume decimal, that is, they are continuous variable. They are not just whole number. They can be whole number, but they can also assume decimal. Most of the quantitative variables mentioned in medicine and social science, they follow normal distribution like weight, height, hemoglobin concentration, blood sugar, think of even age. They follow normal distribution. But it's possible those things that naturally follow normal distribution in your own data set, they may not follow because of. But naturally, if we have enough in the population, the way they behave in the population, they follow normal distribution in the population. But if you collect your data, maybe because the data is too small, it's not representative, the sample is too small, it's not representative, may not be representative of the population, especially based on the way you selected your sample. That data set may not follow normal distribution, even though that variable may naturally follow normal distribution in the population. So one thing, because when they ask people, what is this normal distribution? So many people, the first thing is that mean, mode, and median are the same. The logic behind it is that when distribution is the pattern of occurrence of a variable. So the pattern of occurrence, the way they occur, either in your sample or in the population. That is, the pattern of occurrence means that when you are talking of quantitative variable now. Quantitative variable like blood sugar. If you measure blood sugar of hundreds of us now, how will it be? How many people will have value around 40, around 40 something? You know that is it less than 40 is hypoglycemia will come in. I'm talking of millimeter or milligram per dl now. So if let's say around 50, 40 something 50, only few people will have that blood sugar of 40 something. Normal people that is not in coma, that's as we are in this class now, we take our blood sugar, only few. Okay, let me take something that is very easy to explain it. Let's talk about our weight. If we take weight of adults, as we are here, we take our weight. Only few people will be measuring adult that will be 40 something kg. Few. Then if you move higher to 45, more people will be halfway 45 than 40. If you go to around 50, more people will weigh 50 more than 45. So as you are going higher with the value, more people in the population, the frequency increase is increasing. So if you look at this graph now, you know, there's nothing big deal here about the graph you are seeing. What you are seeing is that, let's say we measure our weight along this line, along the horizontal, as it's increasing, you know, the frequency is the height of the graph you are seeing. So where the, let's say this is 40 here, the first dot here, only few people will be 40. So if you put how many of them, where the 40 and the frequency meet will be around this place. If you say 45, it will be more people. So the graph is going up. If you say 50 kilogram, more people, it will be around this place. More people, that's why the graph is going up. If you say 55, it will be more people. Because as the value increases, the number in the population that we have, that way value increase, the frequency will be going up. If you say 60, more people. 75, more people. 65, more people. 70, when you reach 70, maybe we reach the peak here. So after, if you now say people that weigh 75, they may not be as many as people that weigh average 70. So the number of people involved will be decreasing. That's why the graph is going down now. So if you say 75, 80, less number of people. 85, less. 90, less number of people. 100, you know, adults that weigh 100, they are few. 105, they are few. Even if you see 110, they are few in number. So most natural phenomena follow that pattern. As the value increases, the number of people that have the pattern, the number of people that have that value will be increasing until it reaches a point where the number, if the value increases further, the number will begin to go down. So it has been found that in that situation, if it's actually like that, most of the time, if you add all the value together and divide, so for the fact that the value that reach the peak that go down is certain value, let's say for weight 70. The mean, if you add all the value together and divide by the number of people you observe, even if it is population, the number of the population, the mean will be that value, that peak value, the mean will be that value. And if you arrange the value in ascending order or descending order, anyway, if you are trying to, the one you want to know which one in the middle, that value will be the value in the middle. Let's say weight now is, let's say assume is 70 kg. That 70 will be, that is, you arrange them in ascending order, the middle value will be 70, the average, the mean will be 70. So if you see how many people have each value, that 70 will be the one that value, that mean, and the median value will be the one that has the highest frequency. That is, it doesn't really mean most people, but when you now say each value, how many people have each value, that value will be the one that have the highest number of people having the value. That is the mode. So mean, mode, and median are the same in anything that follow normal distribution. And we have already said normal distribution is a continual probability distribution. If you look at it, because it is difficult for people to know the value, you cannot list all the possible value of anything that follow continuous probability distribution, especially not like example of it is normal distribution. You cannot list, you cannot say, okay, how many possible blood sugar, how many possible weights? Can you list it? You cannot list it. These are the possible weights. Because this weight someone can weigh, say, we are just talking of 70, 65, we are just rounding up. Someone can weigh 70.12, another person may weigh 70.13, another person may weigh 7.5, another person may weigh 70.011. You know, even between 70 and 71, infinite number of possible values. It's only that we round it up. So you will see that for continuous probability distribution, it is not even possible for you to know what is the probability of somebody weighing 70 kg. It's not possible because you don't even know, because in probability you have to calculate how many weigh 70 over total number of possible value. Since you cannot know all the possible value, so it's difficult for you to know the probability of a particular value. So it is if you cannot list the probability. It's not possible to know all the possible value. So because of that, you cannot have a table. You cannot have a table that showed all the possible value and now begin to put the percentage. It's not possible. So what you can have is you can plot graph like this. So that is what we call probability density function. So you can plot graph for all the probability distribution anyway, but you can, as I've said before, you can write equation. So 3 things you can use to represent probability distribution: table, graph, equation. But for discrete probability distribution, you can represent discrete probability distribution with all the 3 methods, either equation or table or graph. But for continuous, you can only represent by equation and graph. You cannot represent it by table. You cannot draw a table. I say you are listing all the probability. It's not possible because you don't know all the probability. But because one can just plot graph like this normal distribution. Now, one thing about normal distribution also, you will see that it's bilaterally symmetrical. It's like a bell. The one side is the mirror image of the other. If that is the case, that middle, where the mean mode and medians are, which is the middle, which is the peak of the graph, the line divides the graph into 2 equal halves. So that is why you see 50-50. So it's a logic now. I want you to get from here. Because the area, we know that the probability cannot be more than 1. Ugo, you are making us, please mute yourself. Probability cannot be more than 1. So 1 can be 100%. No, 1 and 100% is the same. Just a matter of multiplying by 100 or dividing by 100. So if I say 1, it means 100%. If I say 80%, it means 0.8. 90% is 0.9. You know that. So when you say probability is 60%, it means 0.6. So probability cannot be more than 1 or more than 100%. So it is really, if you plot a graph of continuous probability distribution, since we cannot use table to do anything with it, if you plot the graph, you just believe that, okay, the graph, the total area under the graph will be 1, which is 100%. And to explain it, there's no other, in fact, there's no other probability density function. I've told you, when you represent probability in a graph, it's called probability density function or mass function. So there's no other probability distribution that can best explain it apart from normal distribution. Since we know in normal distribution now, the area under the graph is, okay, we want to assume is 1. How can we assume it is 1? Since we know that the area is bilaterally symmetrical, that is, if you slash into half in the middle, that middle, the right side is mirror image of the left side. If that's the case, if you divide something, even if it is yam or bread, equally into 2. So one side is half. One side is half also. Irrespective of the former size of your bread, whether it be bread or yam or whatever, or water, or anything you want to divide equally between 2 people, divide into half. So whatever the quantity before, once you can slash it to half, this one has taken 0.5, this has taken 0.5. So 0 to half plus half is equal to 1. Can you see the logic now? So the area, total area offered under probability distribution is 1. Just like we know that the probability, the total probability is 1. Cannot be more than 1. So you can just assume, conceptualize it that even when you represent probability distribution by graph, the total area is 1. It's clear now. Now, we have already established that in normal distribution, mean mode and median is the same. But later we talk about the variance. If it is skewed, or other, like all those other T distribution, chi-square distribution, F distribution, they are skewed. They are not normal. They can only become normal if their degree of freedom increases. They now look like normal. They now approximate normal distribution. They are skewed. So we'll talk later about the skewness. Though in our previous lecture under when we talk about basic concept of statistics and descriptive statistics, probability and normal distribution, we talk about those skewness, where we still make mention of them. But we may not talk much, but we quickly talk about what caused those skewness. If you go and watch all our video, you will see the idea we talk about extensively. You watch that video on probability and normal distribution. We talk about causes of skewness, positive skewness, negative skewness. Now, let's move forward. Now you will see there are many properties we still talking about this normal distribution, but just know that it's bilaterally symmetrical. It's bell shape. Now, but there is something, even though we know that the mean, mode, and median are the same for normal distribution, but there's something that if you plot normal distribution for different variables, for height, for weight, for distance, for IQ, for blood sugar, for whatever, you know, when you plot it, whatever you plot is a function of the unit. In fact, if you want to plot any graph, you must state your scale that 1 centimeter represent 10 units or whatever. If you remember physics those days, when you do physics, you are plotting graph, you have to state your scale, even in geography. Say 1 centimeter represent 1 kilometer, 1 unit or whatever. So when you are drawing it on the paper, you must be able to tell you, okay, the length, 1 centimeter, what does it represent? 1 meter, what does it represent? So it's the same thing, because many of the things we say follow normal distribution, naturally, they are not on the same scale. Like when we are talking of weight now, you'll be talking of 60 kg, 70 kg, 80 kg. When you are talking of height, if you measure it in meter, you'll be talking of 1.75, 1.76, 1.55, 1.67 meter. But if you measure in centimeter, you see, if you come 176, 150, can you see? If you measure height in centimeter, the value you get will be greater than that of the weight. But if you measure height in meter, the value you'll be getting naturally will be smaller, simply 1 point something, 1 point something from the weight. If you measure kilometers, distance travel, so you know what it means. It depends on the distance travel now. If you're talking 1,500 kilometers, 80, something like 80 kilometers can be many kilometers. If you are mentioning if it is hemoglobin concentration, you know. So when you are plotting different things, you will now need different units. Even though if it's normally distributed, it doesn't really remove the fact that mean, mode, and median will be the same or approximately the same. But because of the unit variation in the means of measurement, and which will make you likely to even use different scale to measure it on the, on the paper where you are plotting the graph. It will show you what you are seeing here. Some will bulge out, some will, even though all of them will still be bell shape. A bell shape, bell is different from bell, even though it's bell shape. Some will bulge out, some will be bulge pressed in. So how, why? Because they have different variances. Because they have different variances or standard deviation. So they are, even though the mean, because for that particular data, though the value of the mean or what you get for distance will be different from weight, but we know that for each of them, mean, mode, and median are the same. But you are not going to get, even though it's bell shaped, bilaterally symmetrical, you not get exactly the same graph, just like what you are seeing in the two graphs here now. So you can assume different shape. So to overcome that, because you see now, these things, they have different variability. The two graphs you are seeing, they have different variability. And you can have as many graphs as that, like that. So the intelligent people now say, what shall we do? Intelligent people have a way of solving problems. So in those days, people like Pearson, they now say, what shall we do? Because they said that it was Pearson that first of all talked about standard deviation. So that's okay. What they will do is that instead of us talking about if you are plotting your normal distribution, you plot it with the natural value, like height now. You plot it with centimeter or meter, or instead of you plotting weight with kilometer, kg, or distance with kilometer, or whatever you perceive it by gram per year, you are measuring. Instead of you doing that, there is what we call standard. I say you make it standard. You transform it to make it standard. If the first standardization I first want to talk about, I don't know, yes, when we're talking about distribution was when you express something as percentage, it's a form of standardization. We call it relative frequency. You know that if somebody, you do study now, your sample size is 200. Another person may do the same study, sample size may be 300. Another one may do 500 or 600, different sample size, even some 50, 150, the same type of study. So how could you compare your result? If somebody say in my study, the proportion of I have 120 male, 80 female out of 200. Another person is doing his own, say he has 150 male, 150 female, or 155 male, 145 female. You know, different value. Because they don't have the same sample size. You cannot be quoting, compare 150 with 120. 150 out of what? So unless you put it 150 over 300, multiply that by 100, you are expressing it as percentage. By expressing it as percentage, you have standardized it, you now express that percentage. So somebody will quote his own work, 45% were made. Irrespective of the sample size, you'll be able to compare. Somebody say 45% are made, his own say 55%. You know there's a difference. So when you, one way of standardizing a percentage, but in this case now, it's not percentage. So the intelligent building has to let's standardize. How do we standardize? This first graph you see with blue, that is the normal distribution. That's the graph because this is the mean in the middle, mu, and this is the spread of the graph. You can say, okay, you may want to know the standard deviation. The standard deviation is in row. Can you see how widespread? Well, now, and you have different value for different work. Now, they now try to standardize it so that it will become, this is normal distribution. This is standardized or standard normal distribution, where you now make the mean to be 0 and standard deviation to be 1. It will be 1. We already know that if you plot normal distribution for different variables, if there are 120 variables, they will give you 120 different graphs. But for this, if you transform all of them to standard normal distribution by standardizing, they follow only one. There's only one standard normal distribution. How does it happen? So you see that the mean is 0, the standard deviation is 1, the variance is 1. So how does it happen? Look at the illustration on how they did it. This is an illustration. This is just an hypothetical example. So we have, let's say we have some women that enroll in an exercise program. Please, somebody is making noise.
Sorry.
Please mute yourself anywhere you are. Please, Dr. Ogudeji, please mute yourself. You background.
Sorry.
Noise from your background. So now, so let's say we have women that enroll in an exercise program, and the mean weight of the population of the women is 70 kg. It's an assumption, it's an hypothetical example. And their standard deviation after you have calculated the mean and the standard deviation is 10. So the mean is 70 kg in the population of the women, and the standard deviation is 10 among them. So maybe after when they came for exercise, about some of these people, you know, they have a uniform they used to do exercise. They just post according to their weights. They post for picture. You can see them now. So you will see the standard, the relationship between their mean, the value or the value of each of them, and the standard deviation and what we call Z-score is this. If instead of you to say, oh, let's say number 1 is Eunice, and Eunice is 50 kg. Can you see it's 50 kg? So I say, Eunice is 50 kg. You want to know how many standard deviation away is Eunice from the mean. Once you have already known that the mean is 70, so you now remove 70 from the 50. That's what I illustrate here. Remove 70 from the 50. And now divide by the standard deviation. Can you see? You say 70. That's if you remember when we first of all talked about 2 weeks ago, when I talked about understanding statistics beyond the basic concept, I talked about deviation from the mean. So removing mean from each value is called deviation. You represent mean by the mu, and mean in the population by the mu. X is the value of individual, and rho is the standard deviation in the population. So if you remove mean for this first person from the value and divide by the standard deviation, you will see 50 minus 70 will give you minus 20. If you look at it, because the mean and the value, they are measured in kg. The standard deviation also is measured in kg, the same unit. Both the value and the mean and the kg, we have already talked about it. It's only variance. It's variance that is in square of the, if let's say the variance now will be square kilograms. But in standard deviation we have here. I think I've explained that concept before. Why we go to variance and come back, you square. Because you know that if you remove deviation, if you add all the deviation together, it gives you 0. So when you square deviation, it becomes square deviation. When you calculate your variance for it, the variance will be in square kilogram. So if you calculate the square root, it becomes kilogram, the normal unit of the original value of the weight and this mean. So it's the same thing. Kg now cancel kg. Because when you are dividing two things of the same unit, it will be unitless. It becomes ratio. Ratio is what you get by dividing two quantity of the same unit. So when you cancel kg, cancel kg, it will be minus 20 over 10. Minus 20 over 10 will be minus 2. You do the same thing for this Grace, the second person. 60 minus 70 over 10, it will be minus 10 over 10. It gives you minus 1. So you come to Florence, 70 minus 70 is having the value of the mean. It will be 0. 0 over 10 will be 0. When you now come to Mabel, which is 80 minus 70, it will be 10 over 10, it will be 1. You now come to Jane, which is 90 minus 70, 20 over 10, 2. You will see these people, 50, 60, 70, 80, 90 kg. When you transform it by removing the mean from each of them and divide by the standard deviation, it will give you minus 2, 1, 0, 1, 2. Why 0 here? Let's start with this 0. This 0, it is 0 because this person is having exactly the value of the mean in the population. So it's not different from the population mean. When you remove mean from it, it gives you 0. Whatever you get out, it will be 0. Why this one negative? This one they are negative because you are removing mean from smaller number. When you remove mean from it, will give you negative. Why this one positive? Because you are removing mean from higher number. So the one in the middle have the same value as the mean, so it gives you 0. But the other one less that give you that less than the mean, they give you negative. Those ones that are more than the mean give you positive. So what you have just calculated now is the number of standard deviation away from it, because you remove, you get how far are they away is what you get by removing one from the other, by minusing me from each value. That's how far they are away. But you measure that in kilogram. Oh, it's minus 20 kilogram away or 20 kilogram away. You now divide by the standard deviation. It will give you how many standard deviation inside that difference. How many standard deviation inside that? So this one is telling you that this 90 means that there are 2 standard deviation inside that difference. Because you can have 2 of 10 inside 20. This one, there's only one standard deviation over the because the difference is 10 over 10. This one is the same thing, 1 and 2, but because they are less, the difference is negative difference. That's why you are getting negative value. So the number of standard deviation away from the mean, an observation or a value is called z-score, z-score. That is the origin of the z-score you see. Z-score, that is the z. Z is the value x minus mean over standard deviation. So instead of me to say, oh, this first person I say, oh, is Eunice is 50 kg, I say it's minus 2 standard deviation. The second person I say, oh, Flora is minus 1 standard deviation. This one is 0 standard deviation because it doesn't differ from the mean. That's why it doesn't deviate from the mean. It's the same value as the mean. Then this one is 1 or +1 standard deviation. This is +2 standard deviation. So the pediatrician use it a lot because when children, you are trying to know the appropriate weight and height for children. So they will do one study where they try to see for the age, because children are not like adults. As they are increasing, the weight, the height increasing in age as they are getting older. For that particular age, the weight will be increasing. So the weight, you don't expect 3 years old to weigh the same thing as 5 years old. So if you are trying to study them now, you cannot just say, I calculate the average weight is this. It doesn't make sense because the average weight of what are you trying to tell us? Average weight is this. But whatever, they are not adults. So what do you expect? We have different weight. So what they now do a study for each age now. What should be the average of median weight age? Either mean or median age in weight or height for the age for each particular age. So when they have calculated it, so when the child comes now, you want to know how many standard deviation away. So by removing that average for the population for the particular age from the value of that child and then divide by the standard deviation. When you do that, you'll be able to, this is how many standard deviation away this child is from the normal, from the average in his own age group. So they use it a lot. They now use Z-score. They use this score a lot. So, and that's the only way they can use to describe weight and height of children. So that is just for you to have the understanding of how it's generated. Once it is generated now, instead of you to now plot, so you just change everything you are dealing with, either height, weight, whatever, change it to Z-score, either kilometer, whatever. So it will follow, you just plot it. Instead of you plotting the value, kg, whatever, you plot the standard deviation. It should give you the same shape, but this one is perfect. It's 1, the mean will be 0. You remember that the mean will be concise with the value that once somebody asks the value that is the mean, you remove from it to be 0. So the mean will still be in the middle, like the one you see before. But the middle will be the mean, which is 0. And toward the right side, left side rather, there will be negative value. Those are the values that are less than the mean. Toward the right side, there will be positive value, say standard deviation. Those are values naturally that are more than the mean. So that mean, either it's 70 kg or 120 something, whatever, is represented as 0 here. So while any value above the mean will be positive, any value below the mean will be negative. So but that value above the mean, how many standard deviation away above the mean, that's what we are seeing here. And how many standard deviation we saw are below the mean, that's what you are seeing on this side. So, and it's still bilaterally symmetrical. Now, that is that. So that is what we call standard normal distribution. The other one that you just plot normal distribution for any is just called normal distribution. So we have different normal distribution for each variable, but that standard normal distribution is only one, is universal. So once you convert each value to their Z-score, you follow that standard normal distribution. Now, other truth you want to know about this normal distribution is that it has been proven, study has been done over and over and over, that if you try to see how the value, anything that follow normal distribution, it has been, if you convert to that standard normal distribution now, you will see that 68.27% of your sample or the population, we have a value that will be in between the value that corresponds to -1 standard deviation and the value that corresponds to +1 standard deviation. For example, now for our hypothetical example of this weight we just use now, you know, -1 standard deviation is 60 kg, +1 standard deviation is 80 kg. So what they are saying is that among the adults, 68.27% of the people will have the weight between 60 and 80 kg. That's what they're saying. So if they also say that between -2 and +2 standard deviation, 95.45%. That is, in our hypothetical example now, -2 kg is 50 kg, -2 standard deviation is 50 kg, +2 standard deviation is 90 kg. So 95.45 of those women we have weight between 50 and 90 kg. Can you see the proportion is bigger? You expect that. And 90 kg. Now, let's say we still have some people that are maybe 40 kg, which is -3 standard deviation. In that our example, and 100 kg, that would be +3 standard deviation. So almost all, 99.73 we have that value. So it's natural. So 99.73% of you will have value between -3 and +3 standard deviation. But the statistician, the researcher, they are more interested. If you look at it, all these values, they are not without decimal. Now, the researchers are interested in middle 95% for this -2 to +2. They are not interested much in 95.45. They are interested in the middle 95% sharp, like that. So if you now have 95%, so the extension of that standard deviation will not be up to -2 here. It will not be up to +2 here. It will be 1.96. That's the origin of 1.96. So in between -1.96 standard deviation to +1.96 standard deviation, 95% of the value will be in between those two values. That is the origin you see in your sample size calculation. You know that when you remove 95 from 100, you bring 5. That's why level of confidence is, okay, we are not talking of confidence that better. It's the same thing, correspond with it. Your level of confidence is 95, the remaining 5% will be your level of significance. So you will see that when you are trying to calculate your sample size, you see that 1.96 as the standard deviation. When you say standard normal deviation, just standard deviation. Why they call it standard normal deviation? Because it's a standard. That's why it's not just standard deviation that you measure on a normal scale, on the standard normal distribution scale. That's why they call it standard normal deviation. 1.96 that corresponds with 95% confidence interval. That middle 95% is 1.96 standard deviation, plus or minus 1.96 standard deviation. Now, an example here. Now, if you remember, we said something the other time. I said for continuous probability distribution, which normal distribution is one of them, it is not possible for you to even know that what is the probability of somebody having a particular value. It's not possible. But because you can put it in a graph like this, which is probability density function, you can actually say what proportion have a range of a value between a range of value. You can say what proportion have value above certain value, maybe above 50%. What proportion have value between this and this? What proportion have value above this? What proportion have value below this? That's what you can do. Between two values, above a particular value, below a particular value, you can calculate the probability. And how is it done? Look at this slide now. You will see that this one is showing systolic blood pressure in population. The average systolic blood pressure here now, if you look at it, up there, the plots tell the normal distribution. Down, the corresponding standard normal distribution. When you have already transformed those values, the blood pressure, into the Z-score. So up here, normal distribution, down there, the corresponding standard normal distribution for this blood pressure. So you can see if the mean is 0, that shows that the mean for the standard normal distribution is 0. That shows that the mean blood pressure in that population is 100. So if the standard, what is the standard deviation? We know one standard deviation, which is this 68% between -1 and +1. How do you know to calculate the standard deviation? The difference between this 100 and this one standard deviation is 16. That shows that the standard deviation of that blood pressure is 16. The mean is 100 plus or minus 16 standard deviation. If you remove the same 60 from 100, it gives you 84. And if you now come here, you will see the difference between when you now move to 1.96 standard deviation. If you remove this 100 from 131, it gives you 31 instead of 32. If let's say it's 2 standard deviation, it will give you 32, because if the standard deviation is 16, 2 standard deviation will be 32. But because this thing is not to 2 standard deviation is 1.96, that's why it gives you 131. The same thing here, if you are to remove, let's say you want to know the standard deviation on the other side, minus, it's supposed to be 68. Because if you remove 32 from 100, it gives you 68. But because it's not up to minus 2 standard deviation, minus 1.96 standard deviation, it will give you 9, not 68. Now, if you say, what is the probability that somebody have blood pressure above 100? So above 100 is half, because we know that 100 is the mean. And the probability, because half, 50-50, because the total area is 100%. That 100%, which is why it's different from this 100, it just happened that the mean here is 100. So if the total area is 100%, which is 1, so the probability that somebody have blood pressure above 100, which is the mean, above the mean, it means in the middle is 50%, below the mean, 50%. What is the probability that somebody have blood pressure above 130, 135, 131? This 131. You know that this one corresponds from 69 to 131 is the middle 95. So it remains 5%, and that 5% is divided equally on both sides. So if you divide by 5% by 2, that should have 2.5 and 2.5 the area under the graph. So the probability that somebody have blood pressure above 131 will be 0.25, which is 2.5%. It's the same thing, 0.025. Sorry, 0.025, which is 2.5%. The same thing here. What is the probability that somebody has blood pressure below 69? Is 0.025. If they say, what is the probability that somebody has blood pressure above 116? If you already know, okay, let's say blood pressure between 89 and 116, from 69 to 131, that would be 95%. You know, 69 to 131, this area is 95%. If what of between 84 and 116 is 86%, or 68%, we already know that. That 68.27% have value between plus or minus 1 standard deviation. They may ask you what is the probability that somebody has blood pressure between 84 and 131. You know that half of this from here to here is half of 68%. That would be 34%. You know, from here to here is half of 95, which is 47.5. You now add the two together. So that is how you are working with the area to calculate the probability. Now, the last thing we just stopped is, now I told you that apart from skewness, if something is not normally distributed, it may be skewed. Skew means it's not normally distributed. That's just all. So, and the skewness means that instead of the graph to be bilaterally symmetrical like this, where this one half is the mirror image of the other half, it will be flat on one side. Like for this one is flat towards the left. That is negative skewness or left skewed, negative skewness or left skewed. If it is flat towards the right side, that is positive skewness or right skew. So what are those things that cause it? For negative skewness, is both of the two skewness is called by outlier. The meaning of outlier is that when you do your study and all of them, you know, they have value. You now have some, there are some few that have extremely different value. That extremely different value can be extremely small value or extremely big value. For example, as we are here now, in this lecture, somebody may carry the daughter to come and attend lecture. If we are trying to look at what is the mean age or weight or age of we or the people in this lecture, if you say mean weight, let's say weight now, maybe we'll be talking on average weight for adult, okay, 70 kg. But if somebody, some few people brought few of their children to join, children, daughters, sons that are less than 10 years, 5 years, to be part of it. So what the implication of this, if you add it together and divide by total, it will lower the mean because the value are small. They don't contribute much to the total. But when you are dividing, you still count them as complete human being, each of them. So at the end of the day, the mean will be smaller than the median. You know, when we're talking of, when you see the graph, we are moving from right to left to right. When you are plotting graph, the smallest value are around the 0 here, as the value is increasing. So what we are now saying that the mean is smaller. So you get, if you are moving along the graph now, you first of all see the mean before median. Median will be in the middle, mode will be at the peak of the graph. That is negative skewness, because we have some outlier that is extremely small than the rest. But if, let's say, instead of this thing, we now have some big people that join us, big, all those people they call biggie. So if you calculate the mean, what will happen is that the mean will be, because they will contribute much to the total, the mean will be extremely, it will be bigger, it will be on the higher side of the scale. You first of all meet the mode, there's median before the mean will be larger. So it will be flattened to the right. That is positive skewness. When we have outliers that are bigger than the rest, give you positive skewness. But if you have outliers that are smaller than the rest in value, give you negative skewness. That's just it. And you can, then the other thing is how tall and how flat. Sometimes when the variability of what you are measuring is they are very close. There's no variability much. All the value are very close. It will give you something that is narrow like this. That's what's called leptokurtic. Kurtosis is the thickness of the graph. So, but if let's say the value, that shows that the variance and standard deviation are very small because they don't differ much. The value are very close. All the value of the for height now, height is usually close among people down weight. So then, if let's say something like the variability is too much, the variation is too much in the population, it will be flat. That is plateautic. I think we stop here. I've just explained the normal distribution. Normal distribution as a basis for hypothesis testing. That one is under. We'll still talk about that later. That was we discussed under introduction to inferential statistics. When we talk about sampling distribution, we'll still revisit them because those are the issues. Those are the area of transformation from simple thing to more advanced thing that are actually not complex. They are just advanced, not complex. They are very simple, just for you to know the way to go about it. I think we'll stop here so that I don't know if anybody have question. So no chat. Okay, any question? No question. So that should is very, very simple. So if it is very...
Sorry, sir. Good evening.
Good evening.
Lisa, I have a question. My question is, how would you describe the kurtosis for standard normal curve? Thank you, sir.
Yes, there's nothing like that because it's already, if you look at it, it's a standard. It's since the variation is 1, so the kurtosis is how would I put it? Is 0. Yes, I mean the kurtosis is 0, and the skewness is 0. It's not skew. The skewness is 0. The kurtosis is 0. It's not skew. It's not. It doesn't have kurtosis. 0. The value is 0.
Thank you, sir.
Yeah. Any other one? Because that graph is only one. It's the only one that exists in the whole universe. Only one standard normal distribution, and it's in museum. Where is the museum? It's in the mental museum. It's not somewhere else. It's just a concept. It's not a physical museum. So only one standard normal distribution. Okay, any other one? Okay, so if it's so simple, no problem. So if you don't have question, so by next tomorrow we'll talk about another continuous probability distribution. That will be chi-square, so that we're going to see that chi-square is was derived from normal distribution. So I've already told you that the normal distribution is just the one you are seeing, the one that manifests naturally with variable. The underlying under them, that those T, F, chi-square, they are there. It's only that it's just for you to know, for them to manifest. So they are related. Okay, thank you, Prof. Okay, if you don't have question, let me just.
Sorry, I have a question.
Okay.
You said the normal distribution is it a distribution of the sample and not the population? I just want to confirm.
No, when we say normal distribution, yes, both sample and the population also can follow. Yes, I mean now. So it is for both sample and population. But for those chi-square, it's only sampling distribution that follow chi-square, because those variables, they say they don't follow the chi-square. Because the chi-square is something you summarize. But this Z now, you can calculate Z even for each person. I don't know if you can calculate this Z for each person, like your weight, like I calculate Z for. But you don't calculate chi-square for one person. It's a group. When you're analyzing, it's a group, it's a sample. It's a sample you calculate it for. I don't know if you understand me now. Then the same thing with F, the same with T. You are looking at difference between two samples. That's T. The same thing with F. But this normal distribution, it goes both for sample and for variable. That's why we say that that's one that actually occurs naturally, that comes out. That most some variable follow it naturally the way it is.
Thank you.
So
sir.
we talk much about that because when we discuss that sampling distribution we talk about central limit theorem. You go to see, it will be clear to you that for normal distribution, variable follow it, sample follow it. Why the other one is sample that follow them? Is it clear?
Yes, sir. Very clear, sir.
Yeah. Any other one? Okay. There's no. Let me off the recording.